In today's Proof Without Words series, we are going to take a look at integration by parts. Most of us are familiar with this formula, which gives an easy way of integrating quite a lot of complicated expressions. As for the proof, your teachers might tell you that it is a direct consequence of the product rule. Using the fact that integration undoes differentiation, we can integrate both sides of the expression given by the product rule, and out comes the result. While loosely speaking, this is correct, it feels somewhat unsatisfying. In particular, we use the fact that integration is an antiderivative, which requires the Fundamental Theorem of Calculus. The proof we present below requires no such assumption, and as you will see, is purely geometric and deeply satisfying. Before we take a look at the proof, let me introduce the concept of parameterisation. In our usual two-dimensional graph, we are used to having two axes, x and y, where we usually use the y-axis to express the values which a function of x takes. We could have y equals x squared or x cubed, for example. However, what if I would like to keep track of more variables? Let's say, I would like to keep track of the motion of an ant on a plane from time 0 to time t. We have three variables to account for: the x-coordinate of the ant, the y-coordinate of the ant, and of course, time itself. The problem of representing this on a two-dimensional graph, of course, is that we only have two axes. If we let time be the x-axis, you have only another one axis left for either the x-coordinate or y-coordinate. Another more natural way to do this is, of course, to let the x-coordinate and y-coordinate be represented on their respective axes and forego the representation of time on the axis and index the x and y value by time. As the ant moves, it will trace out a path in real time. The time serves as an intrinsic variable which will control the values of x and y at any given time, but we wouldn't be able to figure out its value by just reading the x and y axis. Back to our diagram for the proof. Let's suppose we have two functions f and g, which we intend to parameterize using the variable x. In the movement of n example I show you above, f would be the x-coordinate of the ant, while g would be the y-coordinate, and x would be the time. So let's say, when x is 0, f0 is 1, and g0 is 2, the point 1, 2 will be plotted on the graph, with the x-axis representing the value of f0 and y-axis representing the value of g0. We can continue further by incrementing our x little by little and plot the respective values of f and g on the graph, which allows us to observe how f and g vary with the change in x. In the diagram, we let u equals fx and v equals gx for simplicity. If you look at the graph, fix 2 points A and B and choose to look at their pairs of points FAGA and FBGB, we can see that the shaded area, labeled capital A, is just the integral of u dv, with lower limit of the integral at GA and its upper limit at GB, or in this case, R and S as denoted by the diagram. This is because we are integrating over the v-axis, or summing up little horizontal strips of rectangles with width delta v under the curve of function f, or u. Similarly, if you look at the shaded area labeled capital B, we are now integrating over the u-axis, or summing over little vertical strips of rectangles under the curve of g, or v. So the expression for this area equals the integral of v du, with lower limit p and upper limit q. If we add these two areas up, we basically get the area of the large triangle QS minus of the area of the small rectangle, which is PR. This gives the second equation as desired. To get the final equation, we just do a substitution, so the du and dv are replaced by dx. Doing this allows us to put in the lower and upper limits of the integral, which are a and b respectively. A slight rearrangement gives the final result we desire. That concludes our Proof Without Word episode this time round. I hope you have learned something, and see you in the next video.